Awesome. So, welcome everyone to our introduction for the hackathon session next weekend in Barcelona. This initiative is part of the CISPA European AI and Cybersecurity Hackathon Championship. And before we go into the details of the presentation, let us just quickly introduce ourselves.
Okay, so my name is Adam Dziedzic, and then how I really see myself is that I am a researcher who travels the world to work on the cutting edge of AI research, and we are focused primarily on trustworthy, secure, safe AI. So in my case, currently I am faculty member at CISPA Helmut Center, where I co-lead the group with Franziska. And before joining CISPA, I was also a postdoctoral fellow at the University of Toronto and Veterinary Institute. In Toronto, also I work on the aspects of transformative machine learning, and then I did my PhD in the US at the University of Chicago. And during my time in the US, also I work at Google, Microsoft Research. And sorry, I think the slides are as usual on their own, just playing. So let me just go back. And um, apart from that, also I work in many other companies like investment banks, and also I did my studies at DTU, EPFL, and also did some research at CERN in Geneva.
As of me, I am as well a faculty at the CISPA Center for Information Security. And before that, I've also been in Toronto, in the University of Toronto and the Vector Institute. And I obtained my PhD in Berlin. And I've also done research days quite around the world. So it's very exciting. So to let you know about the next part about us is CISPA, our institute. And CISPA is a research center which is located in Saarbrücken. This is here, like in the center of Europe, basically at the border with France and Luxembourg. And we are a very international research institute with more than 40 faculty from 66 different nations. And what we are particularly proud of at CISPA is that if you look at CS ranking, which is the world's ranking for CS institutions, then CISPA is number one in the category cybersecurity. And this means here you can really do world-class research, competing and basically outperforming the top-notch US universities. As we said, Adam and I, we co-lead a group at CISPA, namely the SprintML-Lab. Sprint stands for Secure, Private, Robust, Interpretable, and Trustworthy. And our 20 PhD students and postdocs are also supporting us in the hackathon, and you will be meeting some of them at the local hub. So, as for this local hub, we'll be in Barcelona meeting you on Saturday, Sunday. And this local hub is part of a larger initiative, namely the Grand European AI and Cybersecurity Hackathon Championship. And the three winning teams among you will be getting invited to the final like here at CISPA. And so basically we were like in total we'll be in six different places. And from all the places, the three winning teams, they will get a like ticket to come and visit us for the final, and there you'll be competing. All teams who make it that far will be getting a 400 euro cash prize already. And if you then are among the top three of all the winners, then you will be having like basically like a higher cash prize. And as for the schedule, this is still a schedule from like our general runabout, where we start on Saturday at 11 roughly. And then we have an opening. Actually, this time we don't have the keynote, so we'll send you the updated schedule. But then at 12:30, after we have introduced you to the tasks and to the computer infrastructure, then the hackathon will begin. And during the day, we'll be hacking. In the evening, we'll have dinner delivered. And then usually people stay the whole night at the location to solve the tasks and to then like just compete and get the first place. In the morning, we'll have breakfast delivered, so you don't need to care for food at all. It's taken care of. And then around 12:30, the hackathon will end, and the solutions will be basically evaluated. And the top six teams among every participant, they will be presenting their solutions. And the presentations will give another ranking that will show basically like in addition to the task, how well you have presented, and there this will yield then the final ranking. And eventually we'll have the award ceremony where we announce the results. If you haven't yet, we strongly encourage you to join our Discord channel. And our Discord channel is supposed to support us not only before, but also during the hackathon. So all the announcement will be made there, and everything, every question that you have, you can have there. And also, if you're still looking for a teammate, so you're registered, but you don't know yet whom you should compete with, then you can also go to this Discord and find a teammate there among other participants. We usually recommend being in teams of 3 to 4 people. So if you're, for example, also a team with 2 people only, and there is a person who's still looking for a team, we would highly encourage you taking them in just to have higher chances because we'll be solving 3 tasks. And there can be helpful to be more people. As of the task will be evaluated against the leaderboard. And this leaderboard basically is a live scoring. So whenever you solve something, then your solution will be evaluated and then we'll be displaying the score. And there's some particularity about it. Inspired by machine learning, we basically don't display to you yet the full score, like the final score, but we divided our evaluation data into 70% validation and 30% test data. So during the hackathon, you'll be seeing your solution on the 70%, and then at 12:30 on Sunday, we'll be switching to the 30% to see basically how well your solutions generalize. And eventually, like the scoreboard will give us an intuition on like who are the top 6 people, and those will then be presenting their solutions in the session.
So maybe at this point, are there any questions regarding this part of the session? You can either ask the question through the chat, or if you want, you can also unmute yourself and just ask the question. Okay, I think that as of now
Otherwise,
there are no questions.
yeah,
So I think that we can move to the
let's do it.
part on the tasks, right?
Yeah, because why we're here today is to basically give you a head start. So I think it's great that you already are engaged and you want to learn what is awaiting you for the hackathon. And while we'll not be disclosing the full tasks that we'll be solving, that is on the day itself to give everybody an equal starting point, but we will be introducing some research background. So from this, you will have a starting point which research directions you can look into or which papers potentially to then like be better off for the hackathon itself. And at the end, we'll also be talking about the compute infrastructure. So this will give you a head start to set yourself up. So let's just dive in. And one part of the hackathon that will be interesting for you are privacy attacks. Privacy attacks in machine learning are something that is actually becoming more and more common. And why they are such a problem is because in databases, everybody understood if we have a database and there is a data point inside, well, like information about this data point is clearly there. But in machine learning, it's not that clear because you do have your training images and then you train a machine learning model on them, and the model is supposed to predict your label. For the dog here, it correctly predicts dog. But for the other two, for the cat and for Alice, it also predicts dog and Bob, and that is incorrect. So to make the model better in training, we backpropagate this loss here through the model, and the model learns based on the training data. But there is a problem with that, namely the training data gets kind of incorporated in the model. So the data or the model can retain some information about the data. And if the model can retain the data, then this data can also potentially leak. And now is the question, where can that data leak? Well, of course, it can leak while you're updating based on the data, hence during training. So an adversary who can watch the model being trained could learn something about the private data. The data could also leak from the model parameters. Somebody who's very smart and analyzes the model parameters could get some findings on the data itself. Or the predictions themselves, they could also reveal the information on the private training data. And where basically data can leak also depends on the knowledge that adversaries have. So you could imagine an adversary who knows everything about your model architecture, your data attributes, even the data distribution and the hyperparameters. The only thing they don't know is what the private data is. And then there's also the question, what are their capacities? Can they just observe your model? Or can they, for example, manipulate the training process or change or observe the parameters? And there we usually distinguish between two type of attackers, namely the white box attacker. So basically we have a trusted environment where the data is stored. So the adversary cannot see the data, but they can freely interact with the model, see the weights, and this allows often for stronger attacks. On the other hand, you have a black box attacker, and the black box attacker just gets access to a model. And from that model, they're supposed to be looking into the model outputs only. So they don't have access to the model internals, but they just look at the predictions. And during the hackathon, this will be one of our main setups. Now let's look into what adversaries can do once they get access to the model and its predictions. And one thing, for example, is so-called attribute inference attack, where the goal is to disclose a secret attribute. Let's say we have Alice here in the training data of her health insurance. So Alice has some public attributes that are known. For example, she's on a social media and she has disclosed some information like her name, her age, and her height. And now there is a sensitive attribute that her health insurance would like to know, namely whether or not Alice is a smoker. And because they know that for smokers, the risk for getting, for example, lung cancer is high, and then she would get a worse fare. So once this model now gets trained on Alice's data, then this information that Alice is a smoker is kind of in the model. And how an attacker can handle it to get this information out of the model is that they can use the publicly known attributes, for example, like the name, the age, and the height. And then they can just brute force over the other attribute. For example, they would then append that Alice is a smoker, and then they would predict the risk, and the confidence of the model would be 0.74. Not too bad, but now they could also see what happens if they actually put in that Alice is a smoker here. What then would happen would be that the confidence is 0.99, so the model is much more confident. And this tells the attacker that they probably guessed the attribute correctly and that Alice is a smoker. So this sensitive information basically leaked. Now, why is that happening? That is because in machine learning, when models are trained on some sensitive data, the models retain this data more. So this data point where Alice is there with the attribute smoker yes is more familiar to the model because it has seen that already. Like the public information and then smoker no, this combination the model hasn't seen yet. But the other combination it has seen and therefore it has a higher confidence, hence fueling this attack. But there are other types of attacks that attackers can run, which go beyond the individual data point and attack more of the data distribution. For example, there's so-called property inference, which is supposed to disclose some sensitive training data distribution. You can think about a company that like trains data on their users, that trains models on their users, and this company really doesn't want to know people, what is the fraction of female and male users. Or you could think about a hospital that trains on their patients database and there is a certain fraction of cancer patients inside, but they don't want to disclose that to not have additional information leak. So these kind of questions are subject to so-called property inference. And the naive thing that an attacker in property inference can do is to just generate different types of so-called shadow data sets with different distributions. Let's say they want to find out what's the distribution between men and women. So they curate many data sets where there are varying fractions of these different classes here. And then they train so-called shadow models on that. The shadow models can have, for example, the same architecture like the original model that they want to learn the distribution from. And then they just train the model on that data. And eventually, what they then do is to compare the model behavior, for example, on the data itself, with the behavior of the shadow model to find the most similar one. And for example, in this case, this might leak this kind of distribution. And if we look back what the initial distribution here was, that seems correct. So by that, the attacker then has basically successfully inferred the property of the whole training data set. Are there any questions about that so far? And by the way, I'm pretty sure like during the hackathon, you could come up with much smarter solution than this brute force here because that is very expensive because you have to curate the data, you have to train a lot of shadow models, and that is then computationally expensive.
can wait a few seconds. You can also think about this property inference or attribute inference or other privacy attacks.
Yeah, whatever is interesting for you.
Okay, so if there are no questions, we can move on. So now actually it's a topic about watermarking the outputs from generative models. And this is really of great importance nowadays, where models such as GPT or Claude, Llama, they are used by millions, billions of users. And here in this aspect, what is really of interest is was the given text generated or not? So we are asking the question on the source of the given text. Was this text human created or was it generated by a model? So just a very, very, I would say, crash course on how language models work. So actually this is autoregressive paradigm for the predictions, which is also called next token prediction. So here we provide to the LLM as the input this. So this is the so-called prefix. And then model predicts that actually the next token should be is. So then we have the next token being is, and then we move this token is back to the front, and then model predicts the next token. How this really happens to predict the next token is that model internally has a vocabulary of, for example, 50,000 different tokens, and then after this first token is, the model just this, the model then selects one of these next tokens from this vocabulary of, in this case, 50,000 different tokens. And then token next is fine. So basically, model predicts the next token with the highest probability. And here we give an example, very simple one, that the token fine has a likelihood of 0.1, token great has a likelihood of 0.04, and token nice 0.06. So the just disclaimer is that tokens usually do not correspond fully to the words. This is just simplification, but I think it's just too easy to visualize, and for the purpose of the explanation, I think it's a great way to show it. So then you have these initial tokens, the prefix, this is, and then you have this whole vocabulary of all possible tokens, and then essentially what model can do is to choose the token with the highest probability, which is predicted by the model. So now the question is, how can we really uh, divide these tokens in a way that we can watermark these outputs? So what is really the predominant paradigm for watermarking large language models is so-called red-green watermarking. So how it really works conceptually is that we have this vocabulary of 50,000 tokens, and we divide it randomly into the red and green list of tokens. So you can imagine that 25,000 tokens randomly selected is marked as green, and 25,000 of other tokens is marked as red. And what we really do is actually we nudge the model to output primarily the green tokens. So in the normal text, when we consider this different color of the tokens, they are equally likely, meaning that you have this no watermark text on the right-hand side, top part. So if you analyze how many tokens are red, how many tokens are green, so roughly there is same frequency of green, and red tokens. However, if you then consider the watermark text, so this lower part of the right-hand side figure, is that most of these tokens, if you verify them, are coming from the green list, which actually was nudged to during the generation with the watermarking. So in watermark text, these green tokens are much more significantly more likely than the red tokens. So now you can think about this list of possible tokens, and then you have these probabilities for fine, great, and nice. But since the token fine is in the red list, then you would not select that as the next token, but instead of selecting fine, you would select token green. Token green, which is great in this case. So let me give you a small intro to the basic algorithm, how we can really watermark the output text from large language models. So this is a canonical algorithm that you can see probably in many now papers and also even probably textbooks. So you are here operating in so-called hard read list setup, where basically you have to select tokens from the basically green list. So you are given an input prompt, so some prefix of tokens, and then you iteratively have to generate new tokens. So then you apply the language model to all the prior tokens, so the prefix given to you, and then, as we discussed in the previous slides, you just compute probabilities for all possible tokens in the vocabulary. And then, given the hash of the previous token, use this actually hash to generate a random number, which then actually divides this vocabulary into this green and red lists. Then you nudge the um, model to generate tokens from the green list. And then your final output is then evaluated. So we want to check if the given text is generated, watermarked or not, and we perform actually statistical testing. So we have to compute if there is significantly more green tokens than the red tokens. So then we have this uh, if statement, and then if most of these tokens are indeed green, then the text is watermarked, otherwise it is stated as non-watermarked text. Okay, so are there any questions regarding the watermarking? Okay, if not, we can just move on. Let's talk about infrastructure. So during the hackathon, also you'll have to use GPUs to solve the tasks, and we provided GPUs for you. So here it was really for us of a big help to get GPUs from Jülich Computing Center in Germany. And at your actual disposal, we'll be having 160, 800 GPUs in total, and then they are just there for you to work on the tasks. First, you have to log in to Jülich Compute Center. So please follow the slides. We'll send them afterwards, and you can register.
And the important thing is you can also do that already now before the hackathon. So like this takes you some time. And if you do it now rather than on Saturday, then you have all the time on Saturday to work on your tasks and you don't need to waste the time to do this setup for the service now.
Exactly. So why we show it now? So that you can prepare beforehand to work on the tasks on Saturday and really hit the ground running. So then you just go through these slides. I will send them afterwards. You just have to also authenticate yourself. Here we have second factor authentication. You can use one of your favorite tools, for example, Google Authenticator, but whichever you prefer, you can use. You also have to agree to this access level to Jülich, so basically sign that. This is the declaration that you use these resources to work on the tasks. Then you also have to provide a SSH key. You can either use your current SSH key or generate a new one. So basic communication with the Jülich center is secured through SSH. And then here is how to really upload your SSH key. So add this to this field, your public key and option string, and just copy the option string from the above. And options is just for the IP addresses. It'd be good if you know what IP addresses you will be using during the hackathon. So it's actually an important part. Now, it's usually taking about up to 15 minutes to get updated all the servers, and then you can get access to the GPUs. Once this is done, you can just SSH in your command line, specifying which SSH key you use, and then just log in your login. Here's my login, digits 4, but just please use your login at this address for the compute center. Usually we work on these tasks in some environment. Here we recommend Visual Studio Code. Most students work in this environment, but here for the purpose of the hackathon, we recommend using this. We show how to leverage this VS Code for the task solutions, how to solve the tasks. So here you have to first log into the Julish login nodes through SSH. So basically you click here in the bottom left corner. So click there, and then you just have to select SSH host. You can configure the one for Julish. Here you just add this in your standard .ssh config file. Here is the config that should be specified for Julish. The last line, in this case 45, is especially for the Windows users. And then once you added this SSH host, you can just here click Julish, and you will be directly in this login node on Julish. And you can actually open new terminal, and then you can activate the project. So the project for this hackathon is training 2614. You can activate the project, and then there are standard folders like $project, $user, and you will be using them during the hackathon. Now, what we recommend is to use UV to manage Python packages. You can easily install UV and then add the packages. So please follow these instructions. You can just use curl to download and install UV tool. And then this is something that can go into your tilde/.bashrc file. So these are standard export commands that can make your life easier during the hackathon. And some additional commands that show how to initialize the new environment using Python version 3.12. You can add standard packages such as torch by just typing uv add torch. So this is relatively easy with UV. Now, you also have to create during hackathon some submission files, such as this main.sh. This file actually is to run a batch job. So only with this batch job, you'll be able to really access this large-scale GPU infrastructure. So you can also try to understand more how to use Slurm, which is the way how to start jobs on the cluster. And here is how you submit this job. So you just write sbatch main.sh. So you submit your code to run on this large scale cluster. So then you can have per a given request, you will be given 400 GPUs. So this is your time really to use these GPUs and find solutions to the tasks that will be giving you during the hackathon. So are there any questions regarding the schedule for the event or any tasks or infrastructure? Seems to be that everything was clear.
Otherwise, if nothing pops up now, you can also ask on Discord later, and we're happy to help you there.
We'll also actually publish this info session on YouTube very soon, and also send you the slides. So then you can also later on just revisit these slides. You can try out. You can also apply to Julish to get access to this project and get started with preparation to the hackathon. Okay.
Awesome. Thanks for the feedback, by the way. That's very great.
Yeah, thank you so much.
And yeah, we're looking forward to seeing you on Saturday. We'll be there with the whole team. And yeah, we're looking forward to having a lot of fun.
Okay, so we'll stay here a few minutes, but if you don't have any questions, you can just disconnect, and we will see you hopefully in person on Saturday.
All right. Bye.
Okay, see you. Bye.